I want to talk a little bit about exponents and logarithms. So we're going to start with exponents, and this kind of goes back to what we've known about exponents. And really I want to spend some time talking about the graph of an exponential function. So for an exponential function, we might have something like f of x is equal to like 2 to the x. And the point is, it's an exponential function, so what you can do is you can plug in x values and find the corresponding y values. So you can plug in things like 0, 1, and 2. You could also plug in -1 and -2 and just kind of see what's going on there. So 2, this would be 2 to the -2, which is equal to 1 over 2 squared, which is equal to 1/4. This would be 2 to the -1, which is 1/2. 2 to the 0 is 1, 2 to the first is 2, and 2 to the second is 4. So you get a bunch of points, and you can just graph them. And really this is just a exercise in graphing this first part. So 1, 2, 3, 4 goes as high as 4 for us. And this is an exponential function, which are really important when talking about things that grow exponentially. So 2 to the -2 is 1/4. All of a sudden we're to 1/2. We've doubled again, we've doubled again. And what we actually see is that no matter how low you get, say you take 2 to the -1000, so way back there, this is equal to 1 over 2 to the 1000. And 2 to the 1000 is an unbelievably gigantic number, but it's positive. And so you have a positive divided by positive. So it's always going to be positive, but it's going to keep on getting closer and closer to 0 if you go back here. So there's an asymptote of the x-axis. And then what ends up happening then is it's going to shoot up towards infinity, and it's just going to go really, really fast. And now it's not an asymptote, it's just growing so fast it almost looks like it's an asymptote. So one of the things you can ask yourself is like, what if I ever had to do like 2 to the 1.5? You should just know that that's between 2 to the second and 2 to the first. So the 2 to the 1.5 right here, that's going to be in between 2 and 4, somewhere in that range. And so this graph is going to end up looking like this. Other graphs that you could do, or virtually any exponential graph, would be things like, what if I wanted to graph f of x equals, let's say 2 to the x minus 3 plus 5. And what would end up happening then is, if I'm going to graph something like this, I'm going to see that it kind of shifts. That minus 3, so if I have 2 to the x minus h plus k, what it does to the original is it gets shifted h to the right and k up. So one way to do this is to just take the previous graph and move it h units, move it 3 units to the right, move it 5 units up. Personally, that's not the way I would handle it. If I was handling this, I would just kind of pay attention to the fact that if I plug in my normal -2, -1, 0, 1, 2, 3 or something like that, then when I subtract that 3, I'm going to get scooted backwards. So like if I plug in -2, for instance, I'm going to get 2 to the -2 minus 5 plus 5, which is equal to 2 to the -2 minus 3, and I jumped the gun. 2 to the -5 plus 5, which is equal to 1 over 2 to the 5th plus 5, which is equal to 1 over 32 plus 5. Something very, very small, bigger than 5. But that's kind of a pain in the butt. The reason I kind of think of it as a pain in the butt is because I really didn't want to see the 2 to the -5. I wanted to see something more like 2 to the -2 or 2 to the -3 or something like that. So since I'm subtracting the 3 and going backwards, what I can do then instead is jump further to the right. Say I start at something like 0, 1, 2, 3, 4 or something like that. Then when I plug it in, I get 2 to the -3 plus 5, which is equal to 5 1/8. Or I get 2 to the -2 plus 5, which is equal to 5 1/4. Or 2 to the -1 plus 5, which is equal to 5 1/2. Or 2 to the 0 plus 5, which is equal to 6. Or 2 to the first plus 5, which is equal to 7. Right? And so then when I go to graph this, I start to see that trend. and it says 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So that first one is 5 and an eighth. 1, 2, 3, 4, 5 and 1/8. So right here, and it goes up to a quarter, up to a half, and then up to 6, and then up to 7. And what I should actually see then is because it's got shifted up by 5, that plus 5 tells me that the asymptote is actually right there. It's not at 0. And then the graph ends up looking like that. So exponents in their graphs, typically I would just plug in values, but I try to find the values that are going to be nice enough to give me things that are going to, I want to see that jump, right? So I want to see that jump that I usually see. The second thing is, the next thing I want to talk about a little bit is logarithms. So for logarithms, what I really want to talk about in this section is essentially what is a logarithm. So when I'm talking about logarithms, I'm talking about, well, what I want to talk about first is maybe talk about just like square roots. Square roots don't have, I mean, they do deal with logarithms, but really what I want to think about is this idea that, like, if I have 2 to the, well, let's say I have 5 to the second power, so 5 squared. That's equal to 25. Another way to say this is if I take the square root of 25, I get 5. So notice that I have really 3 numbers here. I've got 2, and I've got 5, and I've got 25. And I'm writing something about an exponential identity. That when I take 5 to the second power, I get 25. And when I take the second root of 25, I get 5. But one thing I never talk about is I never put the 5 with the 25, right? So I got 5 and 2 on the left hand side. I got 2 and 25 on the left hand side. So 2 is kind of like the power. 5 is the base. And 25 is what you get. What you get when you take the base of that power. I never really talk about 25 and 5 by themselves and then look for the power. So what about 25 and 5? And what if we look for the power? Try to figure out what the power is. Now we know it's 2 because we have it written down right here. But what if I said, I had like these 3 cards, and I said, oh, the power is, and then I gave you the power. And the base is, and I gave you the base. And the exponent is, and I gave you the exponent. And then it'd be like this really fun game. Maybe I'm biased and thinking it's fun, but it could be this fun game where like 2 of these are filled out and you got to figure out the third one. In fact, let's play it. So if I told you the base is 3 and the power is 2, you would go, oh, well, what's what you get? That'd be 3 to the second power is 9. Or what if I said the power is 3, and what you get is, I'm putting WYG for what you get. What you get is 8. Oh, okay, of course, I would take the third root of 8 is equal to 2. But now, what if I said the base is 5, and what you get is 25, and then you have to say what's the power. Well, you could just think it through. What power do I raise 5 to get 25? Okay, it's 2. But how do you write this? Because we could write 3 to the second power is 9, the third root of 8 is 2. How do we write it when we know these 2 pieces of information? We're looking for the power. That's where logarithms come into play. Logarithms is just another way to write down the information given in an exponential equation, just in a different way. And the way you do it is you say log, you put the base here, and then whatever you're taking the log of. So like the what you get. So the way I would write this down is I'd say the log, base 5 is what we had, base 5, 25 is equal to, and that's what it's saying. It's saying the base is 5, what you get is 25, and then the power is 2. So that's where the exponent goes now. And that's what a logarithm does. So a logarithm allows you to do something like this. So we could try a few of them. First you could say, what's the log base 2 of 8? Oh, well that's 3 because 2 to the third power is equal to 8. And another thing that people like to do is they like to say, oh, let's write down the exponential way to say this. 2 raised to the third is equal to 8, just to check it. What's the log base 5 of 125? Oh, that is also equal to, well, 5 goes to what power to make 125? 3, because 5 times 5 is 5. 25 times 5 is 125, so it's 3. What about the log base, let's say 3 of 20, let's say 81. 3 times 3 is 9, times 3 is 27, times 3 is 81, so it must be 4. That is the power that would go to. So the exponent is on the right hand side, and that's what logs are doing. Once you get a logarithm, the next thing you're going to want to do is see if there are any special rules that describe what's going on with logarithms, or how can we approximate. So let's talk about approximating first. Approximation is nice. So say you want to figure out what is the log base 2 of 9. So you want to figure out what 2 goes to make 9. What power does 2 go to make 9? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's not 3, and it's not 4. But we know it's in between those two things. It's in between log base 2 of 16 and log base 2 of 8. Now log base 2 of 8 is 3, and log base 2 of 16 is 4. So log base 2 of 9 is 3 point something. And that's okay. If we're just trying to approximate it, it's 3 point something, that's a good enough approximation. There are also some pretty cool properties that logarithms have. The first one that I want to talk to you about is that if I have the log base b of m plus log base b of n, so they both have the same base, then this is equal to the log base b of m times n. So this is kind of neat. It allows you to take the sum of logs as the log of the product. Now that's kind of weird, but it's really not that weird, is it? Because if I had 2 to the third power multiplied by 2 to the second power, that's 2 to the 3 plus 2, or 2 to the fifth power. In exponential world, when we multiplied like bases with exponents on them, we added the exponents. In logarithm world, we're kind of doing the opposite. When we add the logarithms, we're going to multiply what you get. In fact, these two actually go hand in hand. They kind of work together because, for the same reason, if the base goes, whatever this happens to be, let's call it like a e for exponent. If base goes to e to get mn, and base goes to like something to get m, and base goes to something to get n, then if I add those two things, then that would be what you get right here. So it actually makes sense that this would be a property. Another property is that if you have the log of m minus log of n is equal to the log of m over n. So that's another one that you end up getting. And finally, if you have p times the log of m, this is equal to the log of m to the p. So these are some properties that you can use. Now you might be wondering how you can use them, and the way that you could use them is if somebody told you some information about a logarithm, then you could actually make some approximations. So let me show you how we can use these properties. Suppose someone told you that the log base 4 of 5 was equal to 1.2, and that the log of base 4 of 10 was equal to 1.7. If somebody told you this, then what would end up happening is you could try to figure out what is the log base 4 of, let's say, what's the log base 4 of 5/4? Well, based on the property, this is the log base 4 of 5 minus the log base 4 of 4. According to the problem, this is 1.2. Log base 4 of 4, what power does 4 go to make 4? It goes to the first. So this is just 0.2. Or you could say, what's the log base 4 of 100? This is the log base 4 of 10 squared, which is 2 times the log base 4 of 10, which is equal to 2 multiplied by 1.7, and that's 3.4. So what you can do is you can look inside here and see if you can make it using products and divisions, rewrite it as a product or a division, and then use the properties tab to kind of break this up into pieces that you can add or subtract. So that's how we can actually use the properties for logarithms. So then the next thing that we want to talk about is how to graph a logarithm. And this really is not half bad, it's just like graphing exponential functions. Let's say you want to graph f of x equal to log base 2 of x. So again, you're going to play the same game. You're going to plug in some x values, you're going to find some y values. But here's the kicker. It's not really that fun to just plug in -2, -1, -0, or just 0. It's better to plug in things that you know the log base 2 of. So you know the log base 2 of 1/2. And you know the log base 2 of 1. And you know the log base 2 of 2 and 4. So when you plug those in, for your y, you get log base 2 of 1/2. What power does 2 go to make 1/2? Well, that's just -1. What power does 2 go to make 1? Well, that's just 0. What about to make 2? That's 1. What about to make 4? That's 2. So now once you graph these, you actually get a picture of what the logarithm looks like. So the point is that on your x-axis, at 1/2 you should be putting -1. So 1/2 would be -1. At 1 you should put 0. At 2 you should put 1. And at 4 you should put 2. And so it ends up looking something like this. One thing you'll notice is that you cannot take the log base 2 of a negative number. The reason is because 2 never goes to a power to make a negative. So this is negative numbers not in the domain. And if it's not in the domain, then it must have some type of asymptote. So the graph actually looks like this has an asymptote on the y-axis. Just like before, if we plug in something different on the inside of that logarithm, you can make the shift. So if I have like f of x equal to log base 3 of x minus 5 plus 7, this actually goes to the right 5 and up 7. But that's not the point. What I would do here is I would say what I want inside of the log, what I like inside the log, and then what do I have to plug in x to make that, and then what's the y value. I would like things that are powers of 3 inside the logarithm, so I would like things like 1 and 3 and 9. So when I plug in x, in order to get 1, I need x minus 5 to equal 1. So really this is the x minus 5. If x minus 5 is equal to 1, then I can plug in x equal to 6, x minus 5 is equal to 3, I'll do 8, x minus 5 equal to 9, I'll do 14. So now if I plug in x equal to 6, I'll get 6 minus 5 is 1, log base 3 of 1 is 0, 0 plus 7 is 7, and it's working out. 8 minus 5 is 3, log base 3 of 3 is 1, 1 plus 7 is 8. 14 minus 5 is 9, log base 3 of 9 is 2, 2 plus 7 is 9. And so the points that I get to plot are 6 and 7, 8, 8, and 14, 9. And I can actually use those to graph.